Welcome to Tech Unplugged, where research and innovation goes off script and technology meets everyday curiosity. Today we're going to be talking about a cutting-edge research sprint exploring robotics in nuclear sites for post-operational cleanout, also known as POCO. This discussion features from a paper called Lessons Learned, a symbiotic autonomous robot ecosystem for nuclear environments, featured within the Institute of Engineering Technology, Cyber Systems and Robotics Journal. Today we're in for an exciting podcast, so please make sure you switch to video if on Spotify, or watch this on our official YouTube channel at tech_unplugged1. Did you know that the UK has 17 major nuclear sites that are all heading through decommissioning? They range from old power stations like Hinkley Point A, through to research centres like Harwell and Dounreay, to the giant Sellafield complex in Cumbria. Together, they represent one of the biggest engineering cleanup challenges in Europe, stretching across decades, costing billions, and requiring technology we're still developing, which will affect future generations. Post-operational cleanout, or POCO, is a vital step in this process, and this is where robotics can be a game changer. The UK currently faces this scenario for their legacy nuclear sites, which basically means nuclear sites which were built in the early days of the nuclear industry. Imagine inheriting a house, but before you can sell or renovate it, you have to remove the asbestos, drain toxic chemicals, and neutralise radiation. That's what nuclear sites today face after they shut down. Post-operational cleanout, or POCO, is that deep clean stage, except it happens in some of the most hazardous environments humans have ever had to deal with. So what exactly is post-operational cleanout? The Post-Operational Cleanout, or POCO programme, was created at Sellafield to establish and ensure consistency in the processes that support both site operations and nuclear decommissioning. This is a critical transitional phase where a nuclear facility, after operations cease, is decontaminated to reduce radiological and chemical hazards, making it safer, cheaper, and faster to maintain or move towards decommissioning. Key activities within POCO can include facility characterization and hazard mapping, removal or stabilization of radioactive chemical contaminants, and then the preparation of the facility for future inspection, maintenance, or dismantling steps. This can ensure that the facility is decommissioned more efficiently and safely. So today within this podcast, we're going to outline the results from a 5-day research sprint at the RACO 1 facility, which stands for Robotics and AI Collaboration Facility based in Cumbria. The teams explored the design and development of a symbiotic autonomous robot ecosystem tailored for navigating and operating in the highly difficult and hazardous environments to conduct post-operational cleanout. Within the podcast, we're going to discuss how the robots collaborate, how they share data, and adapt to the environmental constraints in real time. And within this paper that has been identified, we're going to emphasize a lot of the lessons learned. So for example, challenges in deploying robots into areas with limited accessibility, which can include thick cell walls and narrow positions to move through. Balancing remote deployment within in-situ analysis and decontamination. Within these facilities, they have thick lead walls, so how robots are able to do their navigation, analyse the results, and feed that data back to the human is incredibly important. And then innovation opportunities, which include characterization, data modelling, and hazard mobilization techniques for the robots when navigating around these hazardous environments. So within this research sprint, The universities that featured were the University of Glasgow, the University of Manchester, the University of the West of England, and the Royal Holloway of London, where initial meetings were to bring together interdisciplinary colleagues, robot engineers, nuclear safety experts, data specialists, and lay out the initial challenge. This is where, because we were part of an interdisciplinary team, many team members weren't actually familiar with the nuclear sector or post-operational cleanout and what it actually entails. So this allowed for us to lay the groundwork and ensure that there's a shared understanding so we can all work synchronously together. With respect to the spirit of the project, we ensured that we created clear work packages, which included key identified areas of expertise and areas that we wanted to improve with respect to deploying our robots in the field. This included the network communications and infrastructure work package, the robot fleet and symbiotic systems package, which I was part of, and the digital twins and visualization package. Finally, documentation to ensure that we had conducted the correct literature reviews to know exactly what the state of the art out there was, and domain immersion. The different robotic architectures out there and autonomy protocols that we would be required to follow. Different data capture techniques, mapping and analysis required for the robots to follow through with. And then finally, the deployment logistics, any hardware safety considerations, regulatory compliance that we would also need to follow. And this ensured that we could deploy rapid prototyping, and then ensure as well that we could create iterative feedback loops, and ensure that we were being compliant with the procedure within post-operational cleanout and how we transfer that to a robotic deployment. In terms of logistics and team dynamics, 5 days isn't a very long time to be able to do a research sprint. So of course there was a lot of work that we had done in advance of this sprint. However, within the research sprint, we also conducted frequent stand-ups. This ensured coordination throughout all of our teams. We also encouraged knowledge sharing sessions to be able to rapidly discuss something that has been found and evidence that. And then we also discussed the unknown unknowns. Post-operational cleanout isn't widely understood outside of the nuclear domain. So onboarding was a key operational hurdle which we overcame via these methods. In addition, we built mechanisms for quick alignment. For example, shared glossaries, visual reference models, and hazard mapping workshops that we conducted also. In terms of challenges and adaptations, there's a clear terminology barrier. So we had to explain post-operational cleanout in detail and its importance repeatedly until everyone was aligned. This made sure that we could identify exactly what humans are currently doing within post-operational cleanout, and then identify future opportunities with respect to how our robots can address some of these challenges. As the robotics people knew the different opportunities and barriers that their specific robots face, this was good at identifying hazardous areas where robots can take some of the lead with respect to ensuring safer operations within post-operational cleanout. With respect to access constraints, the nuclear sector has a wide range of entrances, exits, portholes, etc. So, albeit we use commercial off-the-shelf robots for this operation, we had to make sure that the environment that we represented had narrow ports, which were constrained by physical realities of the legacy facilities that exist currently. And the great thing about the RACO 1 facility that we were based in Cumbria is that it's very much a safety-first culture, which is represented exactly within all nuclear sectors. The nuclear sector takes very much a defence-in-depth scenario. So Safety is always the first priority. Any steps that you take to employ a new technology has to have all its risks mitigated. And this was balanced with innovation alongside the regulatory requirements and hazard mitigation alongside the different nuclear methodologies that currently exist. So what did our implementation actually look like? Firstly, we deployed two-wheeled robots to enter the environment and utilize two LiDAR sensors, which stands for light detection and ranging. And we created an accurate 3D map of the area which the two robots were entering. The robots also had a couple of cameras in the front too for teleoperation purposes. Now, within post-operational cleanout, we assumed that we already have a blueprint of the environment, which means that we already have kind of computer-aided design sketches of the floor plan. However, we quickly realized that in post-operational cleanout and when visiting these facilities, that the environment can change, whether that be infrastructural degradation or damage, or maybe someone else has had to visit and conduct a different inspection, which hasn't then fed back into the previous notes, for example. So this was good at being able to validate what was the environment actually looking like currently, and is there any new obstacles that we should be aware of currently? Secondly, we identified areas where the wheeled robots might not be able to access. And so that meant that we had an improved understanding and awareness of the environment and area. This was where we realized we should send in a small unmanned aerial vehicle to be able to fly into the environment and start to assess some of the low areas and then higher areas of the mission environment. The UAV also had a small camera and identified an area which could contain some radioactive waste. Now, this was only from images that we could see a potential leak next to these barrels that we had identified. So what we done was the next step was to send in the Karma robot, which has the name Collaborative Autonomous Robot for Emergency Assistance. And this robot has been designed specifically for radioactive scenarios. The robot has an alpha and beta radioactive sensor on board, alongside a radar, which for this demonstration we installed on board the robot. And the radar sensor, you can get different types of radar sensors. So for this one, we were using a frequency modulated continuous wave radar to be able to identify, is this potential radioactive material a liquid, or is it just a potential mark on the floor or type of shadow, for example? Finally, we then teleoperated a legged robot with a robot manipulator arm to conduct a more detailed investigation of the barrel, to use the sensor to identify any additional leaks which may exist. So within the video, what you're seeing is the quadruped, the Boston Dynamics Spot robot, moving into the facility. Within this scenario, we decided it was actually safer to teleoperate the robot. And the robot collects the beta sensor. And then one limitation of the Karma robot is that the beta sensor is only positioned at the ground level, measuring if there's any radioactive materials on the ground. In this scenario, we were able to move the robot manipulator arm up and down the barrel to be able to assess if there was any more radioactive leaks that may exist at higher areas of the barrel. So with respect to our digital environment, we had digital replicas of our robots positioned within an environment that we had created from the blueprint. So what we can see here is our Karma robot navigating throughout the environment. This would be required to be a very similar position for the robotic platform in the real world versus the digital world. And how we done that was utilizing different point cloud data which the robot was collecting, and then tracking that data and positioning that within our digital environment. Within our digital environment, we were able to utilize different visualization techniques to be able to model exactly different parameters within the inspection mission. And finally, as well, we were able to put ourselves in the robot's footsteps, let's call it, where you can visualize point of view camera footage from the robot for the digital environment, and compare that with the real environment to ensure where we were navigating was correct. And as we can see in this scenario, within our post-operational cleanout operation, we're not always going to be expecting to be navigating in bright, easy environments. I must stress how hazardous and toxic these environments can be. So a lot of them are actually in dark, pitch black environments here. And then finally, what you're seeing is a virtual reality environment where a human can drop in and see some of the different analysis with respect to the robotic mission. And then just finishing up, we can see our improved digital twin interface which came out of this, where you can select different markers for alpha, beta, and gamma radiation which has occurred. There's different icons which look like radiation, flammable materials, corrosive materials, or just general warnings about the area. And down the bottom right, we've got hazard report to be able to quickly, for the human in the loop, to quickly assess what hazards should I prioritize first. And then down the left, keeping a point of view camera from all of our robots conducting their inspection mission. So some key takeaways from our sprint. We highlight the importance of interdisciplinary fluency. The robotics team had to learn about safety constraints, and the nuclear team had to appreciate agile iteration. Robotic solutions must be rooted with site realities. For example, the environment must be representative of a nuclear use case scenario with similar material constraints. Future work should include the deployment of symbiotic robotics, where robots can work together to complete different tasks, as there is challenges for every different type of robot, but also many advantages to having a diverse fleet of robots, whether that be sharing sensors, corroborating different types of results, or large robots to do heavy lifting, small robots to get into confined space scenarios. It's all super important for the nuclear sector. And then next, digital twins are essential in understanding complex environments and how they are set up. When you return to a facility after 3 to 6 months, you cannot expect it to be the exact same setup as previously. Hazardous materials could have leaked and infrastructure could have degraded significantly. So using sensors from different robots to create digital replicas of facilities, to be able to update maps, is all extremely important for the humans to make the correct decisions in where and how they deploy the next set of robots. For end users, confidence is extremely important, especially when it comes to autonomous systems. This is important when considering how nuclear engineers require defense in depth and safety compliance. And what I mean by defense in depth is ensuring that all risk mitigation is in place, iterating very slowly to be able to provide, to corroborate the different results that these robots are improving and producing. This is why different tasks may be associated with different operations, whether it be semi-autonomous robots deployed in place, which have actions of a human teleoperating a robot, or completely autonomous operations, which can be quite difficult for the nuclear sector, as one small error can set off a chain reaction which can be catastrophic. So to recap this podcast, we've discussed how a symbiotic autonomous robot ecosystem can be deployed for post-operational cleanout within the nuclear sector. We've discussed the lived experience of organising a research sprint like this across a wide range of academic institutions. And And a key message, if you take away from this podcast, is bridging complex domains like the nuclear decommissioning and robotics, inspection, maintenance, repair, requires clear communication, shared terminology, and structured planning with a strong safety-first culture. If you've made it this far into the podcast, I'd like to thank you for listening. I want this podcast to inspire future generations of engineers, so please, if you found it useful, share, like, subscribe, so I can keep sharing knowledge. And as ever, if there's a topic that you would like to hear about related to robotics, related to engineering, related to AI, you know where the comment section is, fire it in. Thank you so much for listening. This has been Tech Unplugged.